Hello everyone, I'm excited to present my project on 3-pole bandpass filters. This isn't just about the technicalities of filter design, but a guide into how these small components make big waves in our world of communication and technology. So, let's start with the basics. What are bandpass filters? They are not just any filters, they are the gatekeepers of frequency. They ensure the only signals we need get through, blocking out the noise and interference. Imagine a crowded room where you can only hear the person you want to. That's what these filters do in the electronic world. Bandpass filters play an essential role in our world. They are crucial in clear data transmission and enhancing audio clarity. Whether it's your smartphone, radio, or Wi-Fi router, these filters ensure an uninterrupted and clear communication. In the realm of bandpass filters, our three-pole design stands out for its precise frequency selection. This precision is not just a technical achievement, but a gateway to numerous innovations in telecommunication. Our design features an innovative folded arm resonator, a component that enhances quality while reducing size. This resonator is a testament to our commitment to excellence in filter design, providing both performance and practicality. This project isn't just about designing a filter, our design is relevant to current industry needs and presents a significant introduction into the filtering world. Our primary objective was to design a three-pole bandpass filter with a performance-focused microstrip design. This endeavor addresses the miniaturization requirements of modern communication systems, marking an important milestone in our project. To help us understand the significance of the project and have some brief insight over the areas where bandpass filters are most useful, we will briefly go over some applications. Firstly, in aerospace and defense, it is used there mostly to ensure high-speed connectivity, and in telecommunication it's critical for filtering signals and improving data transfers through fiber optics. Additionally, in optical applications such as in satellite communication channels, it serves as an isolator and a solar radiation blocker. A very important application is in the medical field, where filters has been used in retinal technologies. Also, in gesture recognition and audio processing, which are more of the common applications that we might come across in our day-to-day life. Our project's scope was clearly defined, with a focus on designing a three-pole bandpass filter. We targeted a center frequency of 1 GHz, and our design parameters included the making of a folded arm square open-loop resonator, and also in addition to that, the development of a schematic that included an inductor network admittance inverter instead of the basic parallel inductor capacitor or series inductor capacitor components, pushing the boundaries for traditional filter design. We also aimed for some tangible deliverables, mainly a working prototype for the microstrip made in the layout of ADS software, backed by some comprehensive simulation and performance data to ensure that our design meets the preset parameters. Our filter specifications were carefully planned. We designed a three-pole bandpass filter with an admittance inverter centered at a frequency of 1 GHz and a fractional bandwidth of 6%. Our characteristic impedance will be 50 ohms, and we will be using copper as the conducting material and Rogers RT Duroid 6010 for the dielectric. The shape of our microstrip will be the innovative folded arm square open loop resonator. These specs demonstrate our commitment to precision and efficiency. In our journey to design the three-pole bandpass filter, key tools were our constant companions. A laptop armed with Advanced Design System Software (ADS) was pivotal for design and simulation. Alongside it is a crucial notebook capturing our initial concepts or calculations, bridging the gap between theory and practice. These tools, simple yet powerful, played a crucial role in turning our innovative ideas into tangible, efficient designs. Our research methodology was grounded in solid theory and practical design approaches. We calculated component values based on Chebyshev's filter theory, as this approach guarantees us a rippled bandpass paired with a steeper roll-off rate. We also utilized CAD modeling for the schematic and the microstrip to visualize and verify mathematical calculations made, either for the schematic or the layout of the filter. Most of the theory was revised through lecture notes and also thanks to Dr. Augustine's YouTube channel. Following along for the design of the schematic and the layout was simple, as it made using ADS straightforward, following step by step to guarantee that we minimize the mistakes while designing the project. For the simulation, data collection and physical modeling part of our research methodology, we adopted a comprehensive approach for data collection and simulation. Firstly, we plotted the frequency against the decibel scale for both the schematics, the one with the admittance inverter and the one without the admittance inverter. And the main use for that graph is to make sure that our practical center frequency meets the desired theoretical and calculated one. In addition to that, in the multipole filters, when we start simulating the microstrip, we will use the graph to ensure an acceptable practical coupling, and we will be doing that by using formulas and keep adjusting the distance between the poles until it meets the theoretical calculated one with an acceptable error of plus or minus 1%. We will be displaying the final results using MATLAB software to ensure clarity. The physical modeling approach will follow a calculate, then implement, then adjust approach, where we calculate the initial values and then adjust them until we achieve the preset desired parameters for the coupling and the center frequency of the filter. So finally, but also most importantly, is our project outline. In week 1, we initiated our project with a comprehensive design brief, setting a clear direction for the 3-pole bandpass filter design project by studying the literature and the relevant theory. And after that, by week 6, we delved into some preliminary research and simulations. We employed an agile methodology to adapt quickly to the initial findings and our first experiments with the software. And we could interpret these findings to help us solidify our learnings of the theory and improve our proficiency within ADS. Mid-project, to around weeks 9 to 13, our focus shifted into more of a detailed design and iterative testing. Utilizing a structured approach, we managed our workflow very effectively, ensuring each task was given due attention and making sure to apply all the steps for the design so we could meet our preset parameters for the filter. In the final weeks, we will be conducting some extensive testing and refinements. Regular revision during this phase will help us swiftly address any emerging challenges and revise the theory to make sure that we apply everything the way it should. This will help us guarantee that we will provide a fault-proof design and fine-tune our final outcome of the project or our microstrip design. Our structured yet dynamic timeline ensured that we remained on track, culminating in a successful project completion. At the end, I would like to share my reference list for the information quoted in my presentation, especially Dr. Augustine's YouTube channel and his paper on the folded arm square open loop resonator, which helped a lot as it provided all the relevant information in a concise manner, which made researching for the project much simpler than it would have been. Thank you.